Okay, so I want to talk about what are the applications of your quantum computing and what is needed to get there. And when you read the popular press or the marketing uh, from some startups, then there's lots of hype. But we are at the point now where we understand things much better, and where hype slowly starts to give rise to clarity. There's clarity what's possible and what's needed to get there. So from all the maze of things that you read, that quantum computing will cure cancer, quantum computer will give you better stock market predictions, it will essentially solve any of your problems. We understand now what's real and what's maybe harder. And for that, we first consider what is needed for what we call a practical quantum advance. We need, of course, quantum speed up, meaning that the scaling on the quantum machine is slower than on the classical one. And then as the problem size goes to infinity, the quantum curve will be below the classical one. The quantum will win. The question just is, where is this crossover? And we need this crossover time to be short enough. There's been a book that mentioned that there was a machine that in 7.5 million years calculated the number 42. That's not what we want here. We want that time to be a few days or weeks at most. So what are the applications where there's quantum speed up and the crossover time is short enough to be practical? That, of course, means we need constants, and constants matter ultimately. But that means we also have to make assumptions. And so let me make assumptions that on the classical side are pessimistic. I take a single GPU, and we have tens of thousands of those today, but I take a single GPU, the old generation, the new one is already 6 times faster. And that single GPU can do about 3 times 10 to the 14 floating point operations per second. Classical CMOS technology is just amazing, and that was a challenge for most classical alternatives. Moore's law was just too good. But let's take just a single GPU and let's assume that's our reference standard. And on the quantum side, I'm optimistic. I'm speculating that in the next decades, we'll build a machine with 10,000 logical qubits, all-to-all couplings, 10 microseconds logical cycle time. On that machine, I can do maybe 7,000 operations per second. So we see immediately that just doing a fault-tolerant quantum gate operation is just much more complex than switching a transistor. That comes from the fact that we need many tens of qubits, hundreds of gate operations, and we need to generate the control signals throughout, and just that's how the numbers work out for the processing. And also for I/O, the GPU can read about 10,000 gigabit a second. If you have 10,000 logical qubits, and it takes 10 microseconds for one cycle time, then you can load at most 1 gigabit a second. So I/O is already a factor 10,000 slower. That means all the claims that are being made that quantum computers can help with big data problems because the wave function stores exponential data just ignores the fact that we have to get the data into the qubit. So it's likely not for a big data problem, but for small data problems that are computationally hard. And they exist, but then what is needed now to really overcome this constant slowdown? It seems a bit scary if you compare 7 kiloops to 300 teraops. And just when you then think through what is needed, for example, for Grover's algorithm with a quadratic speedup, where classically I have to do n calls to an oracle, and quantum mechanically only square root of n calls. But if you now put in these numbers, again, that are optimistic quantumly for something we might build in a decade, and pessimistic classically, a simple old GPU, then it turns out if the oracle is a single floating point operation, the crossover time would be 4 months. If the oracle is a simple small function with 1,000 floating point operations, it's centuries. And if it's a problem like protein folding, then it's the age of the universe. And there was the paper by the Google team that just quadratic speedup is not enough. We need more than quadratic speedup. We need more than quartic speedup even to make it real. That means of all of those problems, we say we need to focus on the small data problem with the super polynomial speedup, and then some remain. But most of those are then in the field of quantum simulations. And we all know that this is the application, or one application. When I talk to my team, then many people tell me, wow, that's disappointing. I thought I joined the quantum program because quantum computing will change the world. Now you tell me that the only thing it can do is chemistry, material science, and quantum. Then we tell them that, look, we call the ages of mankind after materials. We talk about the Stone Age and the Bronze Age and the Iron Age and the Silicon Age. So materials are a foundation of mankind. And 96% of all manufacturers' goods rely on chemistry. I just don't know what the 4% are that don't it. And it impacts every single human on the planet. So if we have ways of improving chemistry and science, the impact is huge. Examples are the catalysis. There we have to calculate energy barriers precisely. We often can't do it classically. Quantum computers will help. Where there can be used might be bigger problems. Carbon fixation, helping with climate change mitigation, fertilizer production, clean combustion, clean water, clean air. I think there's just lots there. Then also photochemistry, excitations with the photon, solar panels, photosynthesis. There are many problems there where, again, classically, it's hard. Quantum computers will help. Material science, we talked about the Hubbard model, ITC, but that's relevant. With quantum hardware, again, we can make progress here. So there's a huge range of problems where quantum computers will help and will have a big impact. But what is needed to get there? What's needed to get there is first we look at kind of what are the number of qubits you need and what is the runtime you need. For a simple quantum magnet problem, it's pretty lenient. We need to do only a few 100,000 gate operations on a few hundred qubits. But a few 100,000 gate operations is a bit beyond NISQ. And once you use logical qubits, then you'll need a few 10,000, 100,000. But it can be done, I think, in the next years, one will get there. To study the chemistry problems in a reasonable runtime, we need thousands of logical qubits. Yes, you might think that about 100 logical qubits are enough, but 100 logical qubits are enough to store the wave function. But the runtimes, when you then implement the algorithms, take forever. To make it in a reasonable runtime with the logical cycle time of microseconds, Q1, will need about 1 million physical qubits. When the physical cycle times or the measurement times are more in the tens to hundreds of the microseconds, so when it's slow gates, slow measurements, then the runtimes here look more like years, decades, centuries. That means that then one will need even more qubits to compensate for that. So it's really important to get to qubit technologies here that can scale to the millions with fast gate operations. So that's just what we have to face here. But I think we'll get there, and there have been debates about that already. But then at the same scale of runtimes, maybe be a few more qubits, one can start breaking crypto. That means there are also threats around here with quantum. And the question that I want to talk about now is kind of what do we have to do to enable the beneficial applications while mitigating the risk. Because there are people who say quantum computing should be stopped and shut down because it will pose a risk to crypto. And yes, it's true, with Shor's algorithm, if the RSA will be broken, is this will be broken, but it means we have to upgrade our cryptography. We have to just make it quantum resistant and quantum safe. So I'd say we should not stop working on quantum, but we just have to double down as the community on really accelerating the transition to quantum safe crypto. And one easy thing one can do right away is wherever possible using symmetric cryptography. There have been claims around often that because one uses Grover's algorithm potentially to break the symmetric key crypto, one will have to double the key size. But I just showed you before that Grover's algorithm will not be practical because of the constants. So it turns out that the current key sizes are totally fine. Grover's algorithm would take about 10 billion years to break it. So it's not a threat. Wherever we can use the symmetric keys, we should, and we use it pretty often in our data centers. For where you need public key crypto, the answer is just let us accelerate the transition to the post-quantum crypto. There are timelines in Europe and the US and in China. I think we should just move as fast as possible on that. Then I got the algorithm there. We know how to mitigate the risk. We just have to implement it. That will take a decade, but I hope it will also take a decade to get to a billion qubit quantum computer. But there's more to it, namely the beneficial applications, as mentioned before, that we want to enable. They are in chemistry and in material science. And we all know that since a century and more, chemistry is just intrinsically dual use. Every material, every chemical has dual use. The Alfred Nobel story, the dynamite is famous, the monkey of the scientists. And chemistry has faced the problem always that it's intrinsically dual use. There's no single chemical almost that cannot be used for bad purposes. And so if we now, with quantum computers, have a disruptive impact on chemistry and can enable new applications in chemistry and in the material sciences, then that's something we have to think about. The crypto threat, we know how to mitigate. The dual use issue is a bit more complex. But it's not a quantum specific problem. It's a problem that in chemistry was around for centuries, but progress was slow. If using computing, supercomputing, using AI, we can accelerate progress in chemistry, then we have to start thinking now, how do we mitigate that risk? We've just done a study where in the time that it would have taken to study 1,000 materials, we screened 32 million new materials for battery electrolyte. So in 1 week, we could study 32 million materials to find the new compound and then make it. In the same way, people have shown that you can use those tools to easily, within hours or days, find chemical weapons and other things. So this can all be abused for bad. That's a problem we face today. Quantum computing will make it more accurate, but the problem is not a quantum problem. We don't need responsible quantum computing. We say we need principles for responsible computing in general. Whenever we develop a disruptive technology that has dual use, we have to watch out kind of where do we want to use it. And so I think we need framework for responsible computing, be it HPC, AI, or quantum, based on the work that's done on the AI. Thinking about that for the last 2 years, we think that it has to be based on the concept of know your customer. We have to understand the end users, we have to understand the end users, and certain technology we may not want to make available to certain users. That is a subtle issue, and so I think that's something we have to talk about between industry, academia, government, and for the public, including also the church. What are the uses we want to enable? What are the uses that we want to maybe try to limit? That brings me now to the third topic, namely you also need to make sure that the good uses of quantum benefit all. So, and what can we do to enable access to quantum for all? The rich countries have money, have funding. We heard billions. When you look at the map of where quantum money is spent, then most of the map of the world is white. There's lots of money in certain countries, but most of the world has no funding for quantum, or minimal. And that's where I worked with the Geneva Science and Diplomacy anticipated to think through what could we do to bring more people into quantum, to give them access to all, and especially the global south. And so in October, we announced in Geneva that CERN will host the Open Quantum Institute to help bring quantum computing applications, teaching, training globally. That helps us because we need the best global talent to really make quantum computing real. And we can make it available globally because we have ways of mitigating the risks. But that will need the whole world to help find teams and processes to enable the good use and to calm down the fearmongers. And I want to end with the video by Chester on the vision they came up with for quantum.